Oh, hey, did you know a yo-yo is a great way to learn about DNA topology? Well, you're about to find out why.
So I don't know how much you know about a yo-yo or not, but one reason it's kind of helpful for understanding DNA topology is it's actually a very similar type of system to DNA. And so in a yo-yo, what you have actually, you may not know this, is you have a single strand of string that's wrapped around itself many times. And this makes this little hoop that you put your yo-yo on when you want to use it and things like that. And the strands here are twisted up. And so that actually means that this little system here is kind of very similar to a little model here for DNA. And so something we can do to kind of show some of those concepts about supercoiling and things like that from DNA topology we were talking about before is to create different amounts of twist in the string and then see what happens when we try to deform and manipulate it. And so we can see here in this system in which the DNA is, or sorry, not the DNA, but this string is sort of at its natural tension point here. If I kind of move it and try to move it around itself, here I'm just deforming it around, we don't really get any supercoiling structures. However, we can introduce more twist into the DNA, or rather yo-yo string. Okay, and so what I've done over here is that I've taken that yo-yo string and I've added a whole bunch of additional twist into the string so that now it's overwound relative to its natural resting state. And so this is something that would correspond to a linking number in that is greater than the natural linking number of the string. And so you might even be able to notice that just looking at the string itself, it looks much more wound up. And what you'll see is if I try now to bend or manipulate this structure, because it's overwound, as I do so, it leads to the formation of these supercoils. And so these are positive supercoils, the plectinine type structures that we're seeing here. And these are a consequence of what happens when we try to change the different, when we are being overwound relative to our natural frequency, our natural linking number. Okay. Now we can also do this in the other direction. Okay, and so now you see another configuration of the yo-yo string, which sort of models our DNA. And in this case, what I've done is I've gone ahead and massively underwind the string relative to the natural twist that was put in there. And so you can even see this is very loose. We can see this big old hoop here. And just like before, what we'll see is that if I try to bend or deform this structure now, once again, we get the formation of these supercoils. And in this case, these structures are negative supercoils because our linking number is below the natural linking number for this string. And so hopefully one thing you can see is that if I try to bring this material together, it actually compacts up much more cleanly. So if we started with an extended structure, we start to bring it together, these supercoils that form in the yo-yo string end up making the structure overall more compact than it would be otherwise. So if you want to try this for yourself, you don't necessarily need a yo-yo. I just happen to have one because I like yo-yos. But you can try out this for yourself with a rubber band or a piece of string. All you have to do is introduce twist and either over twist or under twist the system and watch what happens as you try to do the deformations. And I hope from this you'll see that the concept of the DNA topology, while it seems a little bit mathematical and could seem confusing, it really is just something that is a phenomena that occurs when you try to deform a structure above or below its natural twist. And I hope from these demos you can see how this might be a nice way to compact all of this material down. And so this is really what's going to happen in our genomes to help get the DNA nicely compacted.